Our speaker today took his BS in physics at Caltech in 1942 and his PhD from Caltech in 1948. I believe he came to Schenectady in the early 1940s and then went back to take his PhD at Caltech. But since about 1950 or 51, he's been a Schenectady resident, working at General Electric Research Laboratory and Corporate Research and Development, primarily interested in semiconductors. Those of you a little older may remember that the 1950s was the time when the transistor was discovered and when there was a great deal of interest in extending our understanding of the solid state, and particularly the use of germanium and silicon. Dr. Hall was investigating methods of purifying germanium and developing processes for getting very highly pure germanium crystals. In 1962, he led a group of researchers that first achieved coherent radiation from semiconductor lasers, and that is going to be the general subject of our talk today. Later, he became interested in pure germanium needed to make high-resolution gamma-ray detectors for gamma-ray spectrometers. Still later in his career, he investigated silicon technology. In 1963, Dr. Hall received the David Sarnoff Award in electronics. In 1970, was elected a Coolidge Fellow of the General Electric Corporate Research and Development. In 1976, he received the Jack A. Morton Award for meritorious achievement in the field of solid-state devices. He was elected to the National Academy of Engineering and to the National Academy of Science in 1978. Last year, in London, Dr. Hall was awarded the Marconi Award for the solid-state laser. This is an award given by the Marconi Foundation. He retired from GE in 1987. We welcome Dr. Robert Hall.
Thank you, Walter. Very kind words. Welcome to all of you, too. I hope many of you were here last week to hear Ivor Viever's talk on chaos and fractals. It was a delightful account of how a simple little mathematical equation could generate those incredibly beautiful and complex Mandelbrot figures. I still don't understand how that happens, but it's a lovely story. Ivor also discussed something called the butterfly effect, where a tiny disturbance someplace around the world can have big impact sometime later in a big complex system, which also to me is a bit of a mystery, but maybe I had something like that happen in my own life, because when I was a small boy, I always enjoyed trying to make things that worked and do things and do experiments, and I had been reading an article in Boy's Life about a group, I think it was at Westinghouse, who were making selenium photocells that transformed sunlight into electricity. And they even thought someday these might be on everybody's rooftop and would supply electricity to their homes. Well, that stirred my imagination. And I thought, gee, that's what I want to be when I grow up. And I made a secret memory tucked away in my mind of the kind of person who did this. They were called electrical engineers. I was too shy to tell my parents or anybody else about my ambition, but I thought that's what I'm going to be someday. And I actually came pretty close. I had the good fortune to find a job where I got paid to do almost what I would have wanted to do as a hobby, doing R&D in the research lab at Schenectady. Not only that, I got paid for it too. So it's been a lot of fun. And I've had a lot of adventures and excitement. And my topic today is one of these adventures that I had I'd like to tell you about. I came to the research lab in the summer of '48, and it was just settling down when Bell Laboratories announced the discovery of the transistor. And Dr. Hull came to me and he said, you know, it might be a good idea if you'd look into this and see what there is to it. Well, I wasn't really convinced, but I took a look, and by golly, it was interesting. And I've been learning about semiconductors ever since. It's been full of challenges and adventures, and as I said, this talk is about one of those adventures. That was a big scientific bombshell, the announcement of the transistor. It really stirred up the world of physics. And then a decade later, there was another bombshell. Ted Mayman at Hughes Laboratories made the first laser. This was a ruby laser. And he actually did this against the recommendations and advice of his management, who thought this was a nutty project and he shouldn't do it. But he got it to work, and all of a sudden their attitude changed. He was a hero. Well, this discovery of Mayman's was followed shortly by similar announcements from IBM and from Bell Laboratories, and in the following weeks everything on Earth seemed to turn into a laser. There were publications coming out almost weekly of a new kind of laser. Well, this was exciting. Just imagine, all through history, people have been trying to make better light sources, a blazing pine knot or an oil candle or an arc light or an incandescent light bulb or fluorescent lights. And all of these light sources depended upon chaotic events. The atoms were banging around and shaking out some radiation, or there was an arc discharge that produced heat, and some of the heat was turned into light. But it was always an uphill job. The sources were always random events with a broad spectrum of light coming out, and coming out in all directions. In contrast, the laser makes a totally different form of light. It's a single frequency, just a single tone. If you compare a rock concert or something with a flute playing a single note, it's a totally different sensation. And not only that, instead of coming out in all directions, the laser produces a beam coming out in a straight line. It's totally different. And of course this caught the fascination of everybody, and we were all talking about it, but well, I had lots of things I still wanted to do in semiconductors, and I stuck in that field. But we sort of tuned in, you know. It was an exciting topic, and we knew some basic things about lasers. First of all of them, the gas lasers and ruby lasers, involve transitions between very sharp atomic levels, two narrow spectral lines, and the light would make a transition from one energy to the other. And these, invariably, in these lasers were very sharply defined optical or energy levels. They also involved a resonator, a pair of mirrors to bounce the light back and forth between them. You capture the light in here and you bounce it back and forth. It gets amplified and built up. And these mirrors, the Fabry-Perot resonators, were an essential ingredient to the laser. They are what made the light come out as a single frequency. And finally, there was the concept of a population inversion. That's a fancy word, and I'll try to explain that to you later. What it means is you have more excited atoms in their upper levels than you have in their levels they're going to go to, but I'll describe that in a couple of minutes. Well, light is a funny thing. It behaves in strange ways, and electrons do too. There's a problem called the duality paradox. It's a strange kind of phenomenon. I'd like to tell you a little bit about it because light waves have this dual personality, and I'd like to illustrate that. If you go down to the beach and look out at the ocean, you see ocean waves rolling along forever, and there's no doubt about what they are. Those are waves. You see kids playing with a beach ball, that's a discrete object, that's a particle, and you have no doubt about what that is. So you can tell them apart. But at the atomic level, life gets a little bit mixed up. Light has a dual personality. Sometimes it's a wave, sometimes it's a particle. Electrons have the same problem. Sometimes they're nice little green balls, I like to think of them like that, as particles, but then they also have wave properties too. So you have to give them this dual personality. If you ask, where is the light going to go, you describe it in terms of waves. You think of it as moving in waves. And you notice this if you see an oil film on a rainy day in the parking lot that has these bright colors. Those are because of its wave nature. If you look at a soap bubble film, you see these iridescent colors. Those are because of the wave-like properties. The wave, there's only 2 or 3 wavelengths in the thickness of the soap bubble film, and the fact that these waves have a certain wavelength property gives them their colors. They also behave as particles. If you shine light on a metal in a vacuum, it'll shoot out electrons sometimes, photoelectrons. If the light is very dim, you only get a few photoelectrons, but they always come out with the same energy. If you turn the light on brighter, the electrons don't change their energy, you just get more of them. The light is giving up its energy in chunks, in pieces. So in that circumstance, the light is acting like particles. These are called photons. So you have to think of them in these dual personality way. And there's a paradox involved, and I'd like to describe that in the, if I can find my slides here. In the view graph here. It's always a puzzle to get right side up, but I'll try. Okay. Here, the top picture is, can you fix that a little bit? Okay. I'm showing a light source here shining on a slit. The light goes through and it spreads out a little bit by diffraction and makes a smudge here on the right-hand piece of paper. If I look at it from the top, here's a light source. It's sending out waves that go to this slit here, and they produce a little smudgy pattern here that I'm plotting as a sort of a bell-shaped curve. This is what you'd expect by a wave moving through a little gap in the barrier. The waves spread out and form this funny pattern. But now, suppose I have 2 slits, what happens? Then the light comes through here. If I only had 1 slit open, you'd see the same pattern over here. With 2 slits, something funny happens. You get maxima and minima. Now you can put a detector here, something that'll count photons as they come by, and you'll count a lot of them here and none here. But if they're particles, well, a particle can't go through both at once, can it? If you cover up one of these so it only goes through one, you get the broad smudgy pattern. But if you open up both of them, even though the light must go through one or the other, being a particle, you find that nothing lands here anymore. The fact that you opened up both of these means that instead of some particles landing here, now they don't. So somehow this thing which we know behaves like a particle, nevertheless is able to sense both of these slits, and when it comes down here, it knows where to land. This is a baffling thing that I don't think we can understand from our macroscopic way of viewing beach balls and ocean waves, but that's the way things behave at the level of quantum mechanics, at the stage where you have to think about when you try to see how lasers and things like that behave, or atomic phenomena. The second phenomenon I want to mention, it's really more basic to the laser, and that has to do with, whoops, here we go again, how light is created and absorbed. In the top picture here, let's cover up the bottom one for a moment. Here's a photon coming in, a light particle. It hits an atom, and it moves the atom from its ground state, this is an energy diagram, up to a higher level. And then the light photon disappears, and you have an excited atom. And after a decent amount of time, the atom decides to give up its photon again. It drops down to the ground state, and out pops the photon. This is luminescence. That's what happens in fluorescent lights, or in your wristwatch fluorescent dial on your watch. So this is a absorption and creation of light. It happens quite familiarly, but the light comes out in random directions. It's forgotten where it came from, so it doesn't know which direction to leave when it finally goes. But back in 1916, a fellow named Albert Einstein got to thinking about this a little bit more and how light behaves. And he found that there was something else that must happen if you study the situation, and that is a phenomenon called stimulated emission. What happens if a photon comes by and the atom is already excited? In other words, it's ready to drop down, but it hasn't done that yet. It's in its excited state. The photon comes by, and it persuades the atom to drop down to its lower state and give up additional energy. It gives an exact copy of itself. So the original photon forces the atom to go to its lower state, and it duplicates itself, like cloning. It makes an exact duplicate of itself. So it remembers what direction it came in, and the copy that it made has exactly the same energy and exactly the same direction. Now, if you have a whole crystal full of these excited atoms, things like this, then once you've made one pair, they'll meet a few more atoms in their excited states. They'll double again. You get 4, 16, 32, and then zillions of photons. Whoops, I'm done anyhow, so that's okay. So the stimulated emission is something that Einstein figured out must happen, and it's the basis of how a laser works. But it took 40 years before people began to really think seriously about how this phenomenon might be used. But then people began to realize that this could actually be applied, and they began to develop masers. These are in the microwave part of the spectrum. Maser is an acronym. It means microwave amplification by stimulated emission of radiation. So these are radio frequency amplifiers, but based on this phenomenon of stimulated emission. There's another, the term has also been described as a money acquisition scheme for expensive research. Those are, match the term maser also, and I don't know which is right, but there was a lot of work supported in that field, and it may deserve the second acronym even better. Well, making a jump from microwaves to the visible spectrum was a big step. It didn't happen just overnight. People were worrying about it. Charlie Towns had done a lot of work on the theoretical side trying to think of how one could make a maser that worked in the visible part of the spectrum. That would be called a laser because it's light amplification by stimulated emission of radiation. Well, the dark horse in this race was Ted Maiman. He was working at Hughes Laboratories and believed that it should be possible to do this in Ruby, and he did. He got it to work, and off they went. Well, and this stirred up all this excitement that I told you about. And people would come by the laboratory where I was working in semiconductors still, and they'd say, look, you know how to make lots of gadgets with semiconductors. Why don't you figure out how to make a laser? Well, this seemed nutty to me because there are too many reasons against it. First of all, the luminescence that we had ever seen from p-n junctions, you could make light from a p-n junction, but the efficiency was dreadful. It was about a part in, or 10 parts in a million, a part in 100,000. You put 100,000 electrons through to get one light quantum out. So everything we'd worked with up to recently, up to then, in my experience, had been very poor quantum efficiency, and you couldn't afford all those losses. Secondly, semiconductors tend to be strongly absorbing of light. The ruby is a fairly transparent material. The gas lasers, the crystals you see that had been used for making lasers were highly transparent, and you generally thought of long path lengths, centimeters or even a meter or more of path length between the mirrors. And a semiconductor that thick would be totally opaque. You couldn't get light to travel that far in the semiconductor. Another problem was that the gas lasers, the ruby lasers, these things had very sharply defined energy levels. We didn't have that sort of thing in a semiconductor. The semiconductor has broad energy bands, very wide. So we don't have a similar situation at all. And finally, what do you mean by a population inversion in a semiconductor? We didn't have these levels that you could populate upstairs and empty down below. We had broad bands, and usually everything was in the bottom level. Well, I had a visitor from France, Maurice Bernard, who came by, and the French had been doing a lot of thinking about the possibility of using a semiconductor to make a laser. And we would talk about various projects, and he gave me a very nice lecture on the principles that one might use in making a semiconductor laser, and it got me thinking a bit more about it. But at least it clarified some of the concepts, although I remained rather skeptical. But let's see, maybe I can show you a diagram of the way he described it. Am I still unplugged? There we go. Here's the way we thought of a semiconductor p-n junction. A little slower about that. This is called a forbidden gap in a semiconductor, and there are bands where you can have electrons or have electrons either present or missing. This, on one side of the equation, you can fill it full of, one side of the junction, you can fill it full of electrons. You'd have a sea of electrons sitting over here. On the other side, you'd have empty states where they could go to. And if you put a voltage on it, we knew that you could make electrons go across and drop down into the missing states, the lower energy states on the other side. And if you could get so many that all these states were filled and all of these were empty, then you could have what would correspond to a state population inversion, and that's what you'd need for a semiconductor laser. And this is what Maurice Bernard explained to me, and it began to make a little sense if we could get over this problem of the terrible quantum efficiency, the poor efficiency of the semiconductors, and a few other problems. Actually, you don't know how you'd build a structure like that. But at least he did stimulate my thinking, if nothing else. And it also persuaded me to go down to the library and do a little reading to see what other folks had done in trying to make lasers out of semiconductors. Because some men had been thinking seriously about this and had some rather strange schemes cooked up to make a laser, but none of it seemed very realistic to me, so I went back to my semiconductors. Well, in July of 1962, everything changed. I had gone to a conference, one of these informal semiconductor conferences of the specialists in the field, and two of the speakers, one from Lincoln Labs and one from RCA, gave very similar accounts of observing luminescence from a gallium arsenide semiconductor junction that was very intense, and it seemed to be 100% efficient. In other words, every time you send an electron across one of those junctions that I showed, out would pop a photon, a quantum of light, of infrared light, but nevertheless a very efficient conversion of electricity into light, so that somehow this barrier of the poor efficiency seemed to have been overcome. And the second point was that the light was enormously intense. It was so bright that even though the light came out in the infrared, which you can't see, if you looked at these things, you actually got a sensation of red light. Because it was so bright, it was triggering the sensors in your eye, and your eye thought it was seeing red light. And this is really true. It was very bright. If you actually calculate, they claimed they were getting a kilowatt of light per square centimeter from these junctions, which is fantastic. It's actually about as bright in that part of the spectrum as the surface of the sun. It's an incredible amount of energy. Now, they might have been stretching things a little bit. You know, if you're giving an informal talk and you're enthusiastic, you might be overplaying your hand a little bit, but it was clear that these junctions were very efficient and were putting out a tremendous amount of light. Well, that changed the picture completely. I went back home and plugged some of these numbers into some of the analysis, and it became evident that there might be a real possibility of making the laser if you could think of the right geometry. So I did some work on that, did a little thinking, and came up with a scheme that I thought might, let's see if we can get a slide on here. Can you have the lights down a little bit? It seemed to me that there was a possibility of making a structure that might... Anyhow, this was the structure that I dreamed up as a possibility for making a laser. You'll see it's a trapezoidal thing like one of these weightlifters' weights, I guess you could call it. There was a front surface that was to be polished nice and bright and parallel, labeled front surface, and then there's the back side was to be parallel and polished exactly parallel and nice and shiny. The two side surfaces we deliberately made non-parallel because we did not want any light to bounce back and forth in the wrong direction. We wanted to have these front and back faces to be like the mirrors of the familiar gas or ruby lasers. And so we deliberately had them polished and made as carefully parallel as possible. Secondly, we had to prepare this from gallium arsenide, and we had one side N-type, one side P-type, and we had electrodes attached to them, one on top and one on the bottom. Now, the way this was supposed to work is as follows. If you put a voltage across from top to bottom, you make electrons in holes. These are the charge carriers in the semiconductor. You squish them into the central layer, and then this is the active region, a very thin layer, and they're supposed to recombine there and generate this bright light that we'd heard about at the conference. And the light would come out in all different directions, but any light that happened to come out perpendicular to the polished faces, some of it would get reflected and sent back inside and bounce through to the back face and bounce back and forth. And eventually it would build up in strength and should come out from the front and the back sides of this piece of semiconductor. Now normally the lasers we were familiar with had very carefully silvered faces because the amplification was so poor that you need to have it carefully silvered, so it's very highly reflective. But I knew that with so many losses in semiconductors, it wasn't going to matter much how much reflection you got, because if the gain is going to be enough to overcome the natural losses, then just a little bit more will make it act like a laser without worrying about adding any extra reflection at the front and back surfaces. So that was the thing we planned to make into a laser, and I talked to some of the fellows up and down the hall that I knew might be able to help in a project like this. I found several of them seemed very interested and they had the right skills, so I went to my boss and I said, look, here's this story about the efficient light that people are absorbing in semiconductor and gallium arsenide. How about it if we make a try and see if we can make a laser out of it? I explained it's a long shot, it probably won't work, but even if it doesn't work, we'll learn something about this efficient luminescence, which is going to be pretty important anyhow. Well, he gave it his blessing. That was Roy Apker. He said, go ahead, try it. So I got a bunch of guys together and we set to work. We knew that other places had a big head start on us. The folks at Lincoln Lab and at RCA had given these papers. They knew about the luminescence for quite a while, and in all likelihood we're trying to build a laser. So we knew there was a big rush to get this done as quick as possible, so it was a case of full speed ahead and damn the torpedoes. So I had a fellow who had been working with me, Ted Saltis. He's here in the audience, by the way, and he had a lot of experience making things with gallium arsenide because we'd worked with this material before, and we had material around that was already heavily doped as it would need to be for this project. So Ted knew how to put things together like this, these very tiny objects, and he had the right skill for building the things. We had Gunther Fenner, who was very good with electrical equipment. He was willing to set up the pulsar that would be necessary to drive large amounts of current through these. We knew we'd have to inject a tremendous amount of current through them, and this would burn them out and burn them up unless we had very short current pulses. So he would set up the electrical test equipment and some means for observing any luminescence that might come out of these gadgets. Jack Kingsley was a laser specialist, and he was familiar with a lot of the concepts of a laser, and we had a lot of good conversations with him, getting us steered in the right directions on how to observe the phenomena and what were the right things to emphasize in trying to get one to work. Dick Carlson, I think he was going to be here, I hope he's here. He took on the job of diffusing the gallium arsenide, getting the material, and making the PN junctions. So we had a good team together, and we all worked hard on it. And this was in, I guess, July and August of that year. We were getting these things together and trying to test them, and they would burn out one after the other because Gunther was sending these big pulses of current through and nothing good was coming of it. he'd finally crank the current up enough that they'd burn out or explode, and we'd try another one. Well, Ted was getting better and better at making these, Ted saw this, and he got up to number 52, and Gunther was working on that one Friday, and he saw some unusual light patterns coming out, so he didn't know what to make of that. He came in Saturday, and then on Sunday he gave some frantic phone call to my boss, and he says, "You better come over, there's something going on here." It turned out he had one of these, that number 52 that Ted Saltis had made, and it was producing a very unusual pattern of light. Up to a certain level, as he'd turn the pulsar power on higher and higher, it was just a broad, diffuse glow of light coming out. But above a certain level, it suddenly began to develop some structure. So there was something funny going on. And we all came in after that, and we had a very frantic several weeks because we learned that these things really were producing coherent light. We had convincing evidence of it, and all our worries about all the reasons why it wouldn't work sort of evaporated. We had one that really worked. And believe me, that was tremendously exciting. So we set to work trying to get all the information we could. Kingsley was measuring the spectrum and learning about the different modes that popped up and how they behaved. And Ted was making more of these, and they were getting better and better. Some of them were, a lot of them didn't, but at least we were getting some that were working. And we were rushing to get this written up as a paper that we could publish, to get credit for it, and worrying about these guys at RCA and Lincoln Laboratories that were likely to beat us to it. Well, what we didn't know was that there was a group at IBM who had been working on a laser for over a year by now. They had a contract to build a gallium arsenide laser, but they didn't really know how to go about it. They were working on the thing, but didn't have the idea of putting these mirrors on it. They didn't know how to do that. They were observing the light and seeing strange things happening, but hadn't quite tumbled to the idea of putting the mirrors on and getting the light to move back and forth in the proper direction. Well, anyhow, off in October I went down to a meeting in Washington, and part of my project was to hand deliver a bundle of documents to the patent department and get everything signed in to establish our claim to having a patent filed with a patent group down there. And at the same time I attended this conference and was listening to all the late newspapers to see if IBM or RCA or Lincoln Lab were coming up with any surprises that I wouldn't like. Well, nothing turned up. And I remember going to bed in the hotel that night. This was the height of the Cuban Missile Crisis, and I thought, my God, what's going to happen if overnight we get bombed and all this beautiful work is destroyed? It's a strange, weird way of thinking, but I couldn't help wondering if I would be able to wake up in the morning and enjoy this wonderful success that we'd had. Well, the papers came out in the November issue. Our paper appeared in physical review letters, and it was very exciting. But we had another shock because in a companion journal, the Journal of Applied Physics, here was the IBM group. Was something that was very close to a laser. They had observed this stimulated emission and the line narrowing by a tremendous amount, and they were clearly just about one jump away from a true semiconductor laser, and in the public's eye and in most of the scientific press, I think, they are sort of treated as equivalent, and I think is appropriate. They were working and got so close that they were substantially a neck-and-neck race to getting the laser. But it was very exciting to come out and find this, that we got there first. Along with this, we had a fellow at Syracuse, Nick Holoniak, who worked with us quite a bit, and he was familiar with our work. Now, Nick Holoniak loved to make things in the visible. He wanted to see light that he could see with his own eyes, and so he had been working on a companion material, a mixed crystal gallium arsenide phosphide, which had a bigger energy gap, and the light that it produced was in the visible. So he thought if we had succeeded in making a gallium arsenide laser, which was in the infrared, he'd do the same thing in the visible, and by golly, he did. He was a fast worker too, and he came out, and in just a couple of months' time, he had a visible laser working in light that you could actually see. Let me turn on the slides here. Let's see, I guess I forgot to run through my slides here. This is a photograph of one of the lasers that Ted put together. There's two things in the field. One is this trapezoidal affair. That's the laser. You can see its shiny, polished face on one side. And sitting beside it is a grain of salt. That's a piece of salt that you take out of your salt shaker to give you a comparison of the size. And you can even see that it's transparent. So the one that looks like a transparent cube is a piece of table salt, normal salt shaker size salt, and the other one is the things that Ted Salties was putting together, the gallium arsenide laser. And we thought of them as being pretty small, but nowadays there's been a lot of development in semiconductors and especially in these gallium arsenide lasers, and the modern ones that work so much better and where they've solved all the problems I'll tell you about in a minute are really minuscule in comparison with this thing I'm showing you here. This was really a very crude affair, but by golly it worked, and we were just tickled pink about that. This is the group that I was telling you about. Jack Kingsley on the right here, Gunther Finner is looking away, and we're all looking very sad and somber, and I'm not quite sure why, but I think it's because we were posing for another publicity shot. We were fed up with that. We wanted to get back to work and get on with our experiments. This is the cryostat we were using. These lasers had to be cooled to liquid nitrogen temperature, and Jack Kingsley is holding the cryostat, and the thing that the photographer wanted to get a picture of is way down in the bottom, and he was frustrated by not being able to get anything big enough to show in the photograph. Whoops, I'm trying to go forward in these. I tried to get a picture of Ted Saltis, but I'm afraid all I got was his nose, and I apologize publicly, but he's here in the audience, and I hope after my talk, when the lights come on, he'll stand up and take a bow, because he deserves a lot of credit for this work. This photograph was with a different project. This is our high purity germanium project. Somewhere down here is a piece of this very high purity germanium we developed for making nuclear detectors, but that's another story. I think there's maybe another one. This is Nick Holignac's visible laser. This is a color picture he took and sent to me, and he was proud as punch about that, and he deserves it because that was a tremendous job that he did. This was the first visible semiconductor laser. It actually produced this brilliant beam of red light. If you'll notice there's a dim horizontal line going clear across. That's the part of the junction that's putting out spontaneous radiation, and only the central filament going through the laser went above threshold and produced that beam of light that was so intense that it did give a false color in the photograph. I think that's the end of the slides, yeah. So we have the lights back on. Ted, will you stand up and say hello, everybody? That's Ted's Saltis. I think Dick Carlson was going to be here. Did he make it? I don't see him. He said he was going to be here. You all know Dick. He was at the meeting last week for Ivers, and I'm sorry he's not here because I didn't get him in one of the pictures. Well, there has been an interesting chronology since then. You know, things started back with Albert Einstein in 1916. Then there was this big excitement of all the lasers that people began discovering in the early 60s. And a lot of work had to be done to bring this semiconductor laser from the very crude stage where we had left it to the thing that you now see appearing in compact disc players or laser printers or telephone transmitters. You know, when your voice goes over the long-distance telephone, it's converted from electrical signal into an optical signal by a laser and sent over fiber optic cables across the country. So you've all been using lasers whether you knew it or not. But a lot of work had to be done to make these into a useful commercial device. When we left our activity with the field, the lasers had to be cooled at liquid nitrogen temperature. They only worked under very short pulses of electrical current, and they would die very soon after we got them made. The failure was a very severe problem. It had to do with some kind of defect that was created inside the crystal by the very intense radiation. A lot of people worked very hard on this, and they found defects in the material which the light would would cause them to move around, move together, and form precipitates, which would interfere with the light path and cause the laser to cease operating after a while. So it took a lot of hard work to make lasers which were sufficiently stable to be a useful commercial product. But the problem was solved. It wasn't at all clear that it could be, but people did work on this. The people in RCA or Bell Labs especially, and a lot of people in Japan. The Japanese worked very hard on that problem also, and the problem was solved. They also applied these modern technology of integrated circuit photolithography to make very finely detailed structures, so that instead of these big crude things that Ted had made, they made much smaller, very lasers which had a very sharply defined filament down their middle to be the active region. This gave an opportunity for the heat to spread out and be carried away so that they could be operated continuously, and nowadays they're even made to work at room temperature. So you have reliable lasers nowadays that can work at room temperature, and they'll run continuously. And these were the three major steps, and the fellows that developed these deserve a lot of credit. We bowed out of the field at a fairly early stage because these applications were all in the communications field, and GE didn't have much going in communications, so we left those problems up to some other people. A few other little anecdotes you might find interesting. The dead heat in the race between GE and IBM left the patent people in a quandary, because here were two different big companies, each claiming to have invented the same thing. What are they going to do? How do they decide? Do they split the baby down the middle and give half to each parent? Or how do you resolve this? Well, it turned out the way our two patents were written, we had described our laser in terms of band-to-band transitions, and we called it that the light came out in energy slightly bigger than the forbidden gap of the semiconductor. The IBM people described it in terms of a split-off band of acceptors that was broadened, but nevertheless was a little bit different in energy, and the light made a transition from one band to the split-off band, which would give a luminescence a little bit less than the band gap. So they decided, aha, we can distinguish in all the GE claims. They'll say band-to-band radiation bigger than the band gap. IBM can say the same thing, but it has to be less than the band gap. They issued two patents, and they're both considered as valid patents, and they've long since expired. But that was the way, and well, actually, these bands are smeared out so much in reality you can't tell where the bands end anyhow. So it's a matter of legalism, how you distinguish between. But it did satisfy the patent people, and everything got settled. Things are viewed very differently in Germany. There was a question of how the German courts would decide the proper ownership of the patent, and I was asked to go over there and testify, and there they looked at the actual origins, who had made what claims, and which were valid, which were not, and they decided that the IBM structure was not really a laser. It didn't have those mirrors, and various other cases that were brought up in other things in the literature. They finally concluded that GE alone would get the patent rights in Germany. And in order to make the patent examiners in Germany happy about this, I even had to give a lecture in German on how the laser worked. And they were very, very appreciative that I had made the struggle in my very poor German to give this description, and it ended up very happily. So that was a happy ending to that also. There is one other thing that might amuse you. About a year after the gallium arsenide laser made its debut, a group with Tycho Laboratories announced that they had a better one. They had a silicon carbide laser which worked at room temperature. It was continuous, and you could drive it by batteries in just a little matchbox. And they made the headlines in all the newspapers. They were on Time magazine and everything. And it turned out to be that this was a phony. They had misinterpreted some data. They'd gone overboard, and all their claims for a silicon carbide laser went down the drain. And I got involved in debunking this because I could see that the evidence was quite misleading, and they didn't have a laser after all. And I lost any friends I might have ever had with the Tyco organization, but that's another matter. I think that's the end of the story. It's come a long way since then, but thank you for your attention.
Just how expensive, how much money do you have to put into doing this kind of experiment?
Well, I didn't put anything. I mean, how much did the laboratory put in? Well, let's see. There was 5 of us involved. We were working on it for several months. So to get the first one going, that's about a man-year's worth of work, and I guess I figure $50,000 for a man-year.
120.
Well, nowadays.
Yeah.
It's in the good old days.
Yeah.
So that's the order of magnitude to get this invention to its first stage. But then to carry it on beyond that, oh, it's been a tremendous amount of work. There's been hundreds of people, I think, working on that for many years since then to bring it to its modern stage. I don't know quite what your question was directed to, but it took a lot of work to iron out these problems that I described and to get it into a manufacturer product. You know, you've got to make these by the millions, and that's a tough thing to do, to get something that you can manufacture repeatedly with a good yield, with uniform properties, and have it reliable. It took a lot of work.
Of course, the other hidden cost was the fact that the 5 people all were expert in their own field, and it'd take them 5 or 10 years.
Yeah, we had a lot of experience back of that, right.
Yeah.
Yes.
I noticed as you went through the history of the development of the laser with Lehman and Towns and the area that Bell Labs and so on, that no mention was made of Gould, and there has been, of course, this concern about who had the original idea and who should get the patents, and I guess Gould really came out finally on top of that.
I'm not
sure. As I was interested in the development way back then, we didn't hear a word from Gould's work. And yet here he claims that he really had the idea and deserved the credit.
Yeah, I don't know if that's still being debated. He was working on a classified project. In fact, once people found out what he was up to, he wasn't allowed to read his own notebook. This is crazy, well, I don't know. I haven't been involved in that discussion. I've read about it a bit, but don't know firsthand about it. In the case of semiconductors, I do know that there was a Japanese fellow, Nishizawa, who had a Japanese patent for a semiconductor laser, which he took out a year or two before our patent. But his was a very speculative affair. He had some strange ideas. There were actually several people took out patents on semiconductor lasers before ours, but ours worked. And these all had something wrong with them. Nishizawa had some strange ideas about a resonant cavity. He showed a metal box with some funny wire looping into it, and he proposed using tellurium instead of the right semiconductor, gallium arsenide or something which was direct, some semiconductors are suitable, some are not, and he suggested the wrong kind of semiconductor. He had some preliminary ideas. He'd thought about it and took out a patent, but it wasn't a workable patent. Many people have done this. There were half a dozen applications of unworkable laser patents in semiconductors. And the intensity is never enough to be, there is an application, yes. In principle, if you had 1 million or so gallium arsenide lasers, you could pump a crystal of YAG and pump it up to where it would suddenly fire a pulse of green light. And the submarine people are very excited about that kind of thing. And there is work going on to make a tremendous array of gallium arsenide lasers which would pump a crystal of YAG which would produce this pulse of green light. Because green light penetrates seawater a little bit better than other colors, and you might be able to talk to a submarine better. But yes.
Is Star Wars connected in any way to the laser beam?
Pardon?
Star Wars project.
Yes, Star Wars is worried about shooting down missiles, and they have a lot of enormous lasers proposed for this kind of application. There are things called gas dynamic lasers. You have a chemical reaction which releases a tremendous amount of energy. Sometimes it can generate light, and this can be harnessed to produce a pulse of very intense light. These are enormous things, about the size of a locomotive or something that you want to put up in space. They also have some projects on the ground-based, that might try to shoot up and hit a satellite, but with any luck at all, they won't work.
Perhaps a little way down the road, they'll suddenly discover that after all it was something negative about it.
Well, you have to be careful in working with them because of eye damage. If you're working with a pulse laser, for example, or some of the gas lasers are pretty powerful. If you get a light beam in your eye, it can burn a spot in your retina. That's not good. That's a health problem. I've heard of somebody getting his necktie cut off because of a CO2 laser. A piece of glassware fell through the beam and flashed the beam across his shirt and cut off his necktie. But he was lucky he didn't cut something else off. But anyhow.
In the beginning, you mentioned that you were inspired in your work by an article that you read in Voice Lab magazine.
Yes.
On photovoltaics.
Yes.
Along the way, perhaps after you laser work, did you ever reverse your work and think about photovoltaics?
Well, I spent several years, Ted and I both did. He's right behind you there. Yeah, we spent quite a while working on some ideas for making a very efficient silicon photocell. But a lot of people did, and right now oil is too cheap to make photovoltaics that important, but when oil gets scarce, you'll be back looking for good photocells again. It won't be very long, probably.
Well, thank you very much, Bob. And next time we use our CD players, we'll remember that inside there is this particular invention. Thank you very much.
Yep.